Let's consider a slightly more complex example. We have y equals e raised to the power of k times the tangent of the square root of x. And suppose we want to find the derivative of y with respect to x. All right, so again, I'll do this with both bookkeeping methods. First, we'll look at constructing intermediate variables. And then second, we'll just look at the direct sort of unfolding the chain rule. So we have y is equal to a function. Let's let u be whatever function is inside of y. Y, if we stand back and squint and look at this from a distance, this is an exponential function. It's e to a power. So we'll let u equal that power itself. K times the tangent of the square root of x. All right. Now we see this itself is not a single simple function. K is just a constant multiple. That's not really going to make the derivative harder. We'll be able to pass the derivative through that just fine. But we have a tangent of a square root of x. So u is basically a tangent function, and there's an inner function inside of that. So let's let v be the function inside the tangent, which is the square root of x, which we'll recall also as x to the 1/2. If v is the square root of x, then u is k times the tangent of v. And since we have a definition for u as being k times the tangent of v, or k times the tangent of the square root of x, that means that y is equal to e to the power of u. Right? So we're looking for dy by dx. Y depends on u, so we can look at the derivative dy by du. U depends on v, so we have du by dv, and v depends on x, so we have dv by dx. And again, if you think of these as differentials that we can cancel, du over du is 1, dv over dv is 1, this is dy by dx, so that makes good sense. You can see why this is called the chain rule. As we compose more and more functions, they just sort of chain together like this. You could imagine a sort of dependency hierarchy where the function y, the variable y, depends on the variable u, which depends on the variable v, which depends on the variable x, right? We have this chain of dependencies here, and at each link in that chain, a change in one variable causes the variable above it to change by some scaling factor, and this is given by these derivatives here. So as we go along, we just multiply those scaling factors together, and we'll see what we end up with. So let's work these things out. dy by du, so we look for where we have y in terms of u, that's right here. Y is equal to e to the u. The derivative of e to the u with respect to u is just e to the u. That's the natural exponential function. Du by dv, u here is a function of v, so we have k times the tangent. Now the derivative of tangent, we think back to the previous section, and the derivative of tangent is secant squared. So we have k times the secant squared of v. That was du dv. dv by dx, v is equal to x to the 1/2. So when we take its derivative, that is 1/2 x to the negative 1/2. Right? So now we need to start plugging things back in. We have e to the power of u. We want everything in terms of x, so let's use that first version that we have u is equal to k times the tangent of the square root of x. We have times k times the secant squared of v, and v is the square root of x, times 1/2 x to the negative 1/2 power. This works, but we have a fraction, we also have a negative power, we have a mixture of like square root of x and x to the 1/2. Let's actually pull some of these things together. Let's say that we have k times the secant squared of the square root of x divided by, because we have this 1/2, so we can put the 2 in the denominator. Also, this x to the negative 1/2 power is 1 over the square root of x. So we can tuck that 2 radical x into the denominator. That might be a little bit easier to read. And we still have this exponential e to the power of k times the tangent of the square root of x. So this is probably how I would write this. There are plenty of other ways of writing this. If you wanted to, you could basically just leave it pretty much like this, except bring some of the simpler constants out front, right? We probably want to start with like the 1/2 k, whatever, blah, blah, blah. There are a couple of different ways that we could arrange that sort of thing. But that's the general idea there. Now again, these intermediate variables can be very useful for keeping track of things, but it is a little bit cumbersome to write out. So we might instead say that if y equals e to the power of k times the tangent of the square root of x, dy by dx is equal to, well, the outermost function is a natural exponential function. So its derivative is itself, but since it is the exponential of something more complicated than just x, we have to apply the chain rule. Ooh, just d, there we go, d by dx, and take the derivative of what's inside. That is k times the tangent of the square root of x. So we have e to the k tan radical x times, so we take the derivative of what's inside here. There, okay. This is a constant, so that passes through just fine. The derivative of tangent is secant squared. So we have secant squared of whatever we have. But this was more complicated than just x. So we need to take the derivative of what that was. So we have k times the secant squared of the square root of x times the derivative of the square root of x, that's x to the 1/2. So we have our 1/2 x to the negative 1/2. And we've basically gotten to the stage we were at before, but with a bit less writing. And in fact, once you're well practiced with these, you can probably wrap these up into fewer steps. Rather than writing each one, you can multiply as you go and simplify this down with very little writing at all to work this out. So if you do find the intermediate variables helpful for your bookkeeping for now, as you try to get your head around the chain rule, do try to work towards getting away from that. I wouldn't quite call it a crutch. It can be a very useful sort of thing, but you don't want to become permanently dependent on it, let's say, because as expressions get more complex, you'll have more of those things to deal with, and it could become a little bit time-consuming, a little cumbersome, but it'll always work. Also, one question that some students have with the chain rule is they're occasionally uncertain where to stop. Suppose we went an extra step, and we said, okay, so let's then multiply by the derivative of what's inside. But what was inside of the radical x was just x. And the derivative of x with respect to x is just 1, right? So you would have times 1, and there's nowhere further you can go. So if you accidentally take one too many steps on the chain rule, as long as you're doing it correctly, it will basically terminate itself in a natural fashion. You'll just end with times 1, that'll finish it, that doesn't change anything, and that's okay. But we don't need to do that. Once we recognize that we're down to just x, we can leave it alone there. And again, you can simplify that as appropriate. I suppose I could write out what I was talking about before, where you can bring the 1/2. Let's say, actually, probably want to say something like 1/2 k x to the negative 1/2 secant secant squared radical x e to the k tan radical x, something like that. And again, as I did before, you could leave it like this, or you could tuck the fractions down below to make them actual fractions. There's no real reason that I'm putting the secant squared into the numerator and the exponential afterward, except to maybe make it a little bit easier to parse, I suppose. Makes it a little bit clearer that this is the extent of the function and the exponential is not involved in that. Because I suppose the way I wrote it without the parentheses was a little bit ambiguous, so we should have that in there. So this helps keep that separate, and it also gives me a little bit more room for that complicated exponent to breathe rather than tucking the exponential into the numerator, which would make it a little bit harder to read perhaps. But yes. So either way we want to approach this thing, here we have a case where there's actually a composition of 3 functions. We can chain together as many functions as we want or need to, and the chain rule we just keep popping out additional factors of derivatives of what's inside, kind of like those, what are they called, the matryoshka, the Russian stacking dolls, where you open one up and there's a smaller one inside. You just kind of keep popping those out until there aren't any more. And there we go. So hopefully at least one of those bookkeeping methods made sense for you, and you can get started practicing applications of the chain rule.